Hello and welcome to our third lecture. Today I want to talk about moving stuff around in NX Motion and also how you can use 3D contact. So as you can see, I have a setup that you may find in production lines. I have a push rod in the top that I wanted to push the wheel down the ramp, and then I have a robotic arm that I wanted to push the wheel inside the box. Um, Let me run the simulation. We can take a look on the initial condition. If I go to the animation player, we can see. So this is the initial condition for this simulation. The wheel is not in contact with anything and it's falling, and also the push rod and arm are not being driven. So first thing to do is to define contact between the wheel and the ramp. To do so, we need to use 3D contact. Here in 3D contact, you need to select the bodies that are in contact. And first the action body and then the base. Similar to joints, for example, here you usually set the action as the body that moves more. And also you can define these options, which I'm going to explain later. But let's, for now, define the contact and run the simulation again. Now you see that the simulation is running much slower than before because contact is generally a time-taking process. It has its own loop and it needs to be optimized usually. And if we go back to the animation player and check the contact again, so you see here that the wheel starts to shake. And obviously, the default values are not providing a contact that we expect. Let's say I have a wheel is made from aluminum and also the ramp is made of aluminum, so you don't expect this behavior from the contact. So to find out what is wrong with the contact, we need to understand how the software is calculating the contact force. So a contact between two objects can be defined a zero penetration between the objects. So the base of calculating contact force could be the penetration depth. To do that, as you can see, I can apply a force, which is shown in blue here, to push the objects out of each other. But this force should be relative to the penetration depth and other parameters. To do so, most softwares are using a virtual spring between the objects, so it will automatically keep the objects in contact. As you may know, the force in a spring is defined by multiplying a spring stiffness by the displacement of that spring. We can use the same concept here where the spring stiffness or stiffness here is shown on the contact dialog box. And then the displacement is the gap between the objects. But the gap is usually very small in this kind of application or in contact. And that's why we use the stiffness exponent to increase the static or spring force. So if we do that, or if we put a spring between the objects, the result would be something like this, which is not realistic. So that's why we need to add a damper now to damp this vibration and slow down the oscillation. A damper or a damping force is defined by multiplication of a damping constant, which is shown in C, and the speed of movement, which is the derivative of the displacement over time. Here in our application, the displacement is the gap, so we can define the damping force as a damping constant C multiplied by the speed of change of the gap. And the total force between the two objects will be the sum of these two forces. So we specify the damping factor as the material damping here in the contact dialog box. So remember that the damping is always against the displacement of the object, and that's why it's always negative. So increasing the damping coefficient will increase the damping force, and as a result, it damps down the vibration faster. The next one is the friction between the objects. This is similar to the friction inside the joints that we talked before. The contact friction starts finding friction coefficient. And the software is using two friction coefficients, the static and dynamics. So in this example, NX is using a static coefficient if the speed between the two objects is less than hundredths of a millimeters per second. And then it will use dynamic coefficient if the speed reaches 1/10 of a millimeters per second. And in between, it will interpolate linearly. Now let's move to the advanced tab. The options you have in the advanced tab, the default options are usually good enough for any contact simulation. But if you don't get the result as you expect, then you need to change the options here to reach a better contact solution. So let's first start with contact resolution. If you take a look on the simulation we have here on the contact surface, we have a round object on a flat surface. But at least in NX or in any software, there is no round object. Everything is defined with straight lines. As a result, you present a round object by using flat sides or faces. And that's why you need to define a kind of resolution that represents the resolution or the smoothness of that object that you're using in your contact. So in the contact resolution, the first we have plane tolerance factor. This is a factor between 1 and 10, and it sets the resolution of curves on your object. So here you can see two examples on the right. I have a sphere with plane tolerance factor of 2 on the right, and then I have the other one with the factor of 6. And on the top, you can see what is the difference between the real surface and approximated patches based on the tolerance factor. So here, the lower factors means higher resolution. And the factor of 3 is usually good enough for any simulation, and it is not recommended to change this plane factor. If you want higher resolution, you should use maximum facet size factor, which I will explain later. Next one is the bounding buffer length. In a simulation where like this, you have some objects that are not in contact when you start simulation, it doesn't make sense to start the contact loop because the objects are far apart and not even touching. So the software checks the bounding boxes before it starts calculating penetration. If the bounding buffers, here you see the bounding box around the object and then the bounding buffer length, which is a kind of offset from that bounding box. If the bounding boxes are not interfering, the software is not even calculating penetration. So it will run faster, the simulation will run faster, and the software won't calculate the contact loop. And then the last option here is the maximum facet size factor. By changing this factor, you can change the size of the triangles that represent your object inside the contact loop. So here you can see on the left, even if you have a box, you can decrease this factor to increase the resolution of triangle or the number of triangles you want to have on that face. And if you have a sphere, for example, that will also increase the number of triangles and will increase the resolution of your contact. So Here, after the software found out that the bounding boxes are in contact, it will go to the contact boundaries in the top. The software decides what kind of approach it needs to use based on the numbers that you put here. So you have two options here, global maximum penetration and local maximum penetration. And it's usually set to automatic. If you leave it on automatic, it will change on every loop. So it starts by some initial numbers that we see here, and then the software optimizes it based on how the contact is converging. So let's see this example here. If the penetration is bigger than 23, there won't be any contact. So the contact will calculate penetration, but it won't go to the contact loop. But if the penetration is less than this number, it will go to the next stage, which is calculating the local penetration. The next one here in this example is calculated as 5.7. If the penetration, the calculated penetration, is less than 5.7, it will use a local patch-to-patch approach, which is the most accurate approach NX is using, and it takes the most time. But if the penetration is bigger than 5.7, it will use a global patch-to-patch approach, and it won't loop over all the patches or triangles inside the surface. It takes a little bit less time. So you see here, to optimize the contact loop, the software is using different approaches to reach convergence and also save some time. So here, let's see what is the problem again and how we can solve this problem. First, I need to turn on friction. Friction usually stabilizes the contact. Second, the stiffness, the default stiffness and damping needs to be changed based on the material I have here. And you can refer to this manual of NX Motion to find some basic numbers that you can start with to define your contact. Here, for example, I want to use aluminum, an aluminum contact. So drawing aluminum is 18. Here, if you go to the list, and here we have 18 to 18. So I'm going to use these numbers and define the contact. Here I have a stiffness is 34,000. Stiffness exponent is 1.5. The damping factor is 30. And the friction coefficient is okay for now. You can always change the friction coefficient based on the test you are doing in the lab. So let's keep the advanced options same and run the simulation again and see if the result is as expected. Now let's check the result again. So as you can see, we have a better contact now. At least it is working as expected. But you can see that because the resolution is not good enough, it starts to slowly move forward under gravity force. So to change that, I want to increase the resolution a little bit, as long as it's not making the simulation very slow, especially for the action, because the action is round and we need more resolution there. So I changed this to 2. I use the maximum facet size factor as 2 and solve the problem again. Now the simulation is running slightly slower than before, and that's because we increased the resolution on the object. So let's see the results. So here we have a smoother contact now, but still at the end of the simulation, it starts to vibrate, which is not expected. Now we need to go back to the advanced tab And this usually happens because of this automatic change in the global and local maximum penetration approaches. So the software is switching between these two approaches, and that's why it starts to vibrate. So you can see all these solutions in the NX document. It has a troubleshooting table, which is covering most of the problems that you may have in your contact. So to solve this one, we just need to set the global and local maximum penetration to manual, but the values are okay based on the calculation. Then I run the simulation again. So let's see the result. So now the contact is behaving as we expected. There is no vibration and the wheel is actually staying in place. Let's take a closer look. So this is as expected. And now we can define the same contact between the push rod and the arm as well. Let's go back to the home, 3D contact. Now I want the contact between the push rod and the wheel, and also the wheel and the arm. And I'm basically using the same contact information. Here, if you check, I want to use these contact parameters. To do that, I can just copy the parameters and paste the contacts that I already made. So let me hide the contacts. And so now I have defined all the contacts that I need. So let's move to drivers. Here in NX, you have different options to move stuff around. One option is to drive a joint. So if the joint is a movable joint, it's gonna have a driver tab. Here in the driver tab, you can select different types of driving to drive a specific joint. For example, let's take a look at the push rod, which is a slider joint, and here we can drive this slider by using these driver options. The first one is polynomial driving, which you can set some initial displacement, some velocity, and also acceleration. The velocity and acceleration will remain through all this simulation. The next option, which I'm going to use, is harmonic drive. It is defined as a sinusoidal movement. I want to move it by 50 millimeters. I want it to go back and forth 10 times per minute. And I don't need to have any initial displacement or phase angle. The other options are function, so you can use a general function on velocity, displacement, or acceleration. And it's very useful to control objects, and I will talk about it later. The articulation is used for moving joints after solving the problem. So you can click on solve and then you can start to manually move stuff around. But for example, you can't use contact or other options. And the last two are only available for SimCenter 3D Solver and not available in Recorder. So here I want to use harmonic drive with these options. So let's click OK and let's solve the problem. Now let's check the result. So I need to move the push rod faster and maybe add more displacement so it can actually push the wheel down. Here I increase this to 100 millimeters and I make it twice faster than before and solve the problem. Let's take a look at the result now. So this time I think this driver is good enough at least to push the wheel down, and now we need to push the wheel inside the box at this time step. But we don't want to rely on the time step. We want to check that based on the location of the wheel. So to do that, first I need to define a sensor that is sensing the location of the wheel. But let's first see the other options for driving stuff. Here we use the driver tab to drive that specific joint. The problem is that these driver parameters are specific to that joint only. A better option is to use a standalone uh, driver, which you can use it to drive any joint. So here I can select this joint and it will give me the same options here. I will again select the harmonic drive and I will use the same options. And I can name this push run. So I can use this to drive any joint later. And this driver will override the options that I have in the joints driver tab. So I can just turn it off. Here I think I forgot to change the units. And yes, this should be rounds per minute. Let's see the results. We basically have the same result. So next, I want the arm to push the wheel inside the box right on time. So to do that, first I need to define a sensor. And to define a sensor, we need a marker. The first marker I want to put here on the center on this side of the wheel. And let me set it like this. And the coordination is going to be like this. So the X direction is the direction that I care the most. Let's click OK. I need to make this marker bigger so we see what's going on. So now we see the direction. And next I need to define another marker on this arm as well. So I select the marker. For the point, I want the point to be here on the tip of the arm. I go with the between two point option. I want the point to be in the center here. And I want to specify a similar coordinate system as we have on the wheel. I want the X direction to be like this. So I click OK. Now I have two markers. Let me make the other marker bigger as well so we see the coordinate system. So we have two markers with the similar coordinate system. Now I can define a sensor that is measuring X relative displacement between these two markers. I click OK, and now I can solve and take a look on the result. Okay, now let's see what is returning from the sensor. So as we expect, the distance between these two markers is reducing, and then when the wheel is falling, we have an increase in the distance. So let's play the simulation and then we can see the sensor result. So here we have the minimum distance, as you can see here. So here we have the minimum distance when the markers are in front of each other. So I want to trigger the arm when this distance is less than some numbers. So here we can also use the find tracking to find the result step by step. So the minimum based on this step is something between -1 and 9. So I want to define a threshold. If that condition is met, then I want the arm to act. Of course, we also need some time because the wheel is moving fast, so we need to react faster and move the arm faster so it can push the wheel inside. But the problem is that if we move it too fast, it will shoot out the wheel, probably out of the box. Now, how can we drive something by make some decisions? So here I want to define the driver. I want to define a driver on this joint or pin 2 with a motor. With a motor, you can actually drive and control stuff and decide where exactly you want to start driving and when you want to stop it. To do that, I need to first define a motor. I will keep the default values. And then on the signal, you can define a signal that specifies how much voltage is going to the motor. So the signal value is going to be multiplied by the voltage. If you have 1, it means that 24-volt is going to the motor. And the direction always follows the direction of the joint. So here I want to have a closed loop. We have open loop option, which means that you will write it by using a signal and it's not connected to any sensor. The closed loop is where you can connect the signal to a sensor and start some decision making. Here I can tell the arm to start after, for example, 2 seconds based on the simulation. But that's not realistic and it depends on the time step and other conditions that I have in the solution. And it may not work in a realistic setup. So it's better to use the sensor. The sensor value, as we checked, should be somewhere around the 0. So we want it to be 0, so it's not moving. And if the sensor is returning something less than 0, so here we have, I think, negative values. So first, let's fix that. Let's save the motor and then let's go back to this marker. If I change the direction of this marker and solve it again, we're gonna have positive values in the sensor, which makes it easier uh, to use it in a signal. Now let's check the sensor again. Now we start with a positive value, and when it reaches around 0, we want the arm to start movement. Then I can go back again to the driver that I was making. So I canceled the driver, but I still have the motor here. So I start with a new driver. Here I want to drive the pin 2 with a motor. Motor is already selected as we only have one motor. And then I make a new signal. The signal starts from 0. And then I can, if you click here, you actually see the conditions. Here I want to have a sensor-based event. I want it to start if this is less than 0. Let's just start with 0. I don't want any delay, and I want the signal to be 1 if that condition is met. I click OK, and direction seems to be okay. I save here and start the solution. Let's take a look at the results. Let's go to analysis and animation player. The wheel is rolling down as expected, but as you can see here, the arm starts a little bit late. Let me go by steps so we get a slower time. So here the arm is moving later than we need because the wheel is moving fast, the arm is not on time. Now how can we solve that problem? Obviously we need to start the arm a bit faster. To check that, first I need to define another sensor that measures the gap between these two parts, the arm and the wheel. So let's define the new sensor. Now I want to measure the relative Z component between the two objects, which if I show it on the animation player on the top view, here I want to measure this the gap between them. So I can actually check what is the delay and how fast I should move the arm to reach the desirable result. Now I have the new sensor. Let's run and check the results again. Now I have the results, and now we can check the sensors. I have two sensors here. Let me close the rest of these stuff. So the sensor 1 and sensor 2. Sensor 1 is returning the X value as we had before, and sensor 2 is returning a Z value. And since the arm is swinging, after the wheel is gone, we have the swing action. Now the best way to check is to overlay these two results. Let's go to the result tab and curve operation. I want to have one of them here, X and Y. So this is the X shown here. I want to overlay it on this one. So now I have the information that I need. Let's now take a closer look. I can go to the probe mode. So here we have the trigger point, and then the gap starts, and we see we always have a gap of, on the red line, around negative 61, and when the gap is 0, it means that the arm is actually touching the wheel. Let's go with the fine tracking so we can go step by step. So somewhere around, when the red line is around 0, around here. So we need to have hit point around here, which is on 2.2 seconds, but the trigger is 2.1. So 1/10 of a second earlier, if we trigger 1/10 of a second earlier, we're gonna have the right impact. And if we go back 1/10 of a second on 2 seconds here, so this is the point we probably want to have the trigger, and that's where the wheel is around 200 millimeters away from the arm. So Let's just start on 200 millimeters away and then check the result. So let's go to the signal chart, and this is the old signal that I had. So it was less than, if it was less than 0, it triggers. Now I want it to be less than 200, and without a delay we increase the signal and click OK. Now we can run the simulation and check the result. Now let's see the results again. Push rod hitting the wheel, and then it seems that the arm is hitting the wheel a little bit late and also not in the center. So we need to first adjust the arm before we go with the rest of the adjustment. What we can do here is to trace the wheel or the marker. Let me select the marker here and also the arm. And now let's play the animation again. I want to have a trace right in point. So from here we can start to trace. And here we have the hit point. So now I have all these traces which I can use to fix the arm adjustment. We can now go back to the modeling. Here the trace of the marker are shown in these points, and the trace of the arm are in this feature group. I don't want to move these, I just want to move the two arms and the hand. So let me first hide the traces of the arm. I'm going to go back to the arm and the handle. And then I can here adjust to be centered to the point, and as it hits a little bit under the wheel, which works better for us here. So it's now adjusted, and I can go back to the assembly and remove all these traces of the marker and also the traces of the arm. Now it seems that the arm is in the right place. We can go back to the motion, and then we run the simulation again. Then we can adjust the time. Okay, let's check the results. Let's go to animation player. We can, I think, yeah, I left the trace on, but we can go. So here it hits too much, I think, under the wheel. And also it's not fast enough. So we first need to start a bit earlier, start the arm earlier, and also we need to move it faster. So let's readjust the signal. I increase it to 5, and I want it to start a bit earlier. And let me go back and remove all the traces. and also hide the contacts and joints so we have a better view. Can also hide the drivers. So let's solve again. And now I think we could fit the wheel into the box. So if I now define, I didn't define the contact between the wheel and the box because we didn't need the contact. Now I can define the contact between these two and then use the conditions. I think I have the contact already. Let me check. First contact, second. Yes, that's correct. So just need to copy the parameters here and then solve again, and let's see the result. Now let's see the results. So it seems that we have a successful system that can push a product, but we still need to work on it so it moves back on time instead of stopping there. But I want to talk about something else. Now, if we set up a similar system, the timing is probably not gonna work in reality. And the first problem is the friction and contact. So if you want to validate the problem and validate the solution and make sure that it works in reality, first you need to set up the frictions and contact information similar to what you have in reality. So here I used aluminum to aluminum contact, and also I defined some friction in the joint. So you need to make sure that these parameters are similar to what you have in reality. The second problem is air. So we have air drag or drag friction working on a system. And the drag force is defined as this. It's pretty simple. You have the drag related to the density of the fluid, which is air, and it's 1. And then you have the speed of the object, which is the speed of the movement of the rolling wheel. The drag coefficient is defined or measured for different cross sections. You can easily find the drag force for the drag coefficient for regular shapes, and A is the cross section of the area or cross section of the projected area. So what I need here is first the cross section area here, and then I'll also need the velocity of the wheel. So for I can define a sensor that is returning the speed of the movement along the x-axis. So I want to have the absolute velocity along the x-axis, and let's call this Vx. So now I have the velocity. The cross-section area, I can calculate the cross-section area by just checking this part. So the projected area is a rectangle, as you can see here. And if I measure this, the diameter is 200 and the depth is 50. So the area is 1,000th of a meters square. So I have the area and I have the speed. Now I can define the air friction. Remember that there is no air in motion simulation, but it is possible to define a scalar force or a vector force. Since I have the direction now, I can use the vector force and apply a force that is always against the movement. So I go with the magnitude and direction. We can also go with the component because the wheel is always moving along the x direction, or at least that's the direction we have the uh, air resistant. So I go with x and I want to use a function. Let me first select the component and the origin is correct. I want to define a new function, and this function is going to return the drag. So the drag is half of the density of air, the cross-section area, and then the velocity, I can't get it from the sensor Vx, but remember that this is the velocity of the wheel in millimeters per second. I need to divide it by 1000 to have the meters per second, and this is going to be to the power of 2. So with the remaining part is CD, which we can consider 1 for a rectangular shape, and yeah, this is going to be the drag force. Here I think I forgot the multiplication before these terms. So here you see a unit problem. Let me copy so I can keep this. And go back here. So you need to go to the preferences, motion, and ignore units. Now I can go back to the vector force, select this, create a new function, and this is going to be which is correct, and click OK. Can also increase this, and then we have a force against the movement. And now if we click solve, we can see if the air resistance is a big problem or not. Now let's see the results. So we can see a little bit of change between the two results, but it seems that the friction is not going to affect that much, and we have a good solution.